welcome to this problem walkthrough. Today, we'll be tackling problem number 1953, titled Maximum Number of Weeks for Which You Can Work. In this session, we'll explore the problem statement, discuss potential approaches, and dive into solutions step by step. Let's get started. In this problem, we need to figure out how many weeks you can work on a set of projects, given certain constraints. You are provided with an array called milestones, where each element represents the number of tasks in a specific project. You can work on these projects in any order, but there's a catch: you can only work on one task per week, and once you start a project, you must continue working on it every week until it is finished. The goal is to maximize the number of weeks you can work while adhering to these rules. For example, if you have 3 projects with different numbers of tasks, you'll need to carefully alternate between them to avoid leaving tasks unfinished unnecessarily early. The output will be the maximum number of weeks you can work, and we'll determine this through some examples. Let's look at the first example to understand how this works. Consider the input milestones as 1, 2, 3. The output in this case is 6, which means you can work for 6 weeks. Here's how: you start by working on the project with 3 tasks for 1 week, then you switch to the project with 2 tasks, and then to the project with 1 task. After that, you repeat this cycle until all tasks are completed. This ensures that no project is left idle once it is started, and you are able to complete all tasks while maximizing the number of weeks you work. Notice how alternating between projects allows you to stretch the work across multiple weeks. Now, let's consider a slightly different example where the input is 5, 2, 1. Here, the output is 7 weeks. The total number of tasks is 8, but it's not possible to work for all 8 weeks due to the imbalance in the number of tasks across the projects. The largest project, which has 5 tasks, dominates the schedule and cannot be alternated enough with the others. Here's how the work can be distributed: you start with the project with 5 tasks, then move to the one with 2 tasks, then the one with 1 task, and continue alternating as much as possible. By week 7, all tasks in the smaller projects are finished, leaving you unable to continue working since there's no other project to alternate with the largest one. Let's explore a third example where the input is 10, 2, 2. This time, the output is 14 weeks. The total number of tasks is 14, and you are able to achieve this maximum number of weeks by carefully alternating between projects. You start by working on the largest project for 1 week, then switch to one of the smaller projects, and then alternate again. This pattern continues, ensuring that the largest project has enough breaks to avoid dominating the schedule too soon. By distributing the work across all projects in this way, you are able to use all available tasks and stretch the work across 14 weeks. Here's a breakdown of how the weeks are distributed in the third example. You alternate between the largest project and the smaller projects until all tasks are completed. By week 14, all tasks in all 3 projects are finished. Now, let's summarize some important observations about this problem. First, if the largest project has more tasks than the sum of all other projects combined, you won't be able to work for all weeks. This is because the largest project cannot be alternated enough to avoid leaving idle weeks. Second, if no single project dominates in this way, you can work for all weeks, which is equal to the total number of tasks. So, the key is to check whether the largest project dominates the schedule and calculate accordingly. This reduces the problem to a simple comparison and some calculation. To solve the problem of maximizing the number of weeks you can work, one straightforward approach is the brute force method. The intuition here is simple: simulate every possible way to assign tasks across weeks and see which schedule lets you work the longest while ensuring that no 2 consecutive weeks are spent on the same project. To implement this, we can use recursion or backtracking to generate all possible task schedules. For each schedule, we check if it satisfies the constraint, count the valid weeks, and track the maximum. However, the complexity of this approach quickly becomes prohibitive. Since we are dealing with all permutations of task assignments, the time complexity grows factorially with the number of projects, O(n). Additionally, the space complexity is high due to the recursion stack used in generating the permutations. Because of this, the brute force method becomes computationally infeasible for larger inputs, making it unsuitable for practical use in this problem. A more effective solution to this problem is the greedy approach, which is based on a key observation about task distribution. The idea here is that we can maximize the number of weeks worked if no single project dominates the schedule. Here's how it works: if the largest project has fewer tasks than the sum of all other tasks combined, we can alternate between the largest project and others freely without violating constraints. However, if one project has significantly more tasks, the rules force us to stop earlier because we cannot work on the same project in consecutive weeks. Mathematically, let max_tasks represent the maximum number of tasks in any project and total_tasks be the sum of all tasks across all projects. If max_tasks exceeds total_tasks, max_tasks, the maximum number of weeks is limited to 2 * total_tasks, max_tasks, plus 1, or we alternate as much as possible and finish the dominant project last. Otherwise, the maximum number of weeks equals total_tasks, since we can freely alternate tasks. This approach is both time efficient, requiring only O(n) to calculate max_tasks and total_tasks, and space efficient, requiring no additional data structures. While it demands a careful understanding of the problem's constraints, it is a highly efficient solution for large inputs. Another potential approach to solving this problem is using dynamic programming, or DP. In this method, we would maintain a state that tracks the number of tasks left in each project and the last project worked on. This avoids the brute force approach of generating all permutations, but it still has a relatively high complexity of O(n) max_tasks, where max_tasks is the number of tasks in the largest project. While DP is more efficient than brute force in some respects, it is still less efficient than the greedy approach, especially for larger inputs. Additionally, DP introduces more complexity in terms of implementation and debugging, as it requires managing multiple states and transitions. Ultimately, the greedy approach stands out as the chosen strategy because it is far more efficient and elegant. By leveraging the critical insight of comparing max_tasks to total_tasks, max_tasks, we can directly calculate the result without simulating or tracking task assignments. This drastically reduces computational overhead compared to both brute force and DP methods. The greedy approach runs in O(n) time, is easy to implement once understood, and scales well for large inputs, making it the clear choice for this problem. Every approach comes with trade-offs, and the greedy method is no exception. It relies heavily on the correctness of the key observation that the relationship between max_tasks and total_tasks, max_tasks determines the result. This requires a deep understanding of the problem's constraints, and any misunderstanding could lead to errors, particularly in edge cases. On the other hand, alternative methods like dynamic programming offer more generality and flexibility but at the cost of efficiency and simplicity. Ultimately, the greedy approach strikes the best balance between simplicity, efficiency, and correctness for this problem. By focusing on the fundamental properties of the task distribution, it allows us to solve the problem in linear time while avoiding the pitfalls of more complex or computationally expensive methods. This makes the greedy approach the optimal choice for maximizing the number of weeks you can work. To start, let's break down the problem. Our goal is to assign tasks to maximize the number of weeks that can be worked while ensuring that no 2 consecutive weeks are spent on the same project. Imagine you're given a list of projects where each project has a specific number of tasks. For example, if the input is projects equals 3, 2, 1, it means project A has 3 tasks, project B has 2 tasks, and project C has 1 task. The challenge is to distribute these tasks across weeks, respecting the constraint that the same project cannot be worked on in 2 consecutive weeks. Now, to approach this problem systematically, the first step is to define the input and output clearly. The input is the list of available tasks for each project, and the output is the maximum number of weeks worked while satisfying the constraint. Next, sorting the projects by their task count is a natural step. This ensures that the projects with the most tasks are prioritized, as they are likely to have a greater impact on the total number of weeks. For instance, sorting the input projects equals 3, 2, 1 would keep the same order, but for an input like 2, 3, 1, sorting would yield 3, 2, 1. Sorting helps us plan the task distribution more effectively. Now that the projects are sorted, we can turn to the next major step, using an exhaustive search approach. The intuition here is to generate all possible sequences of project assignments, week by week, to find the maximum valid number of weeks. To achieve this, we can use a recursive backtracking function. This function explores all valid sequences by iterating through the projects in each recursive call. Importantly, it skips any project that was assigned in the previous week to ensure the constraint is met. For each valid choice, we deduct one task from the selected project and proceed to the next recursive step. The function also keeps track of the maximum number of valid weeks worked as it explores the different possibilities. To terminate the recursion, the base case is when no tasks remain for any project. At this point, the function simply returns the count of weeks worked up to that point. The recursive backtracking function relies on two key elements: a list called remaining_tasks to keep track of the tasks left for each project, and a variable, last_project, to record which project was assigned in the previous week. By iterating over all projects at each step and applying the constraints, the function systematically explores all potential sequences. Once all possibilities are explored, the maximum count of weeks worked is extracted as the result. To implement this approach, we rely on a couple of key data structures. First, we use an array to represent the number of tasks remaining for each project. For instance, 3, 2, 1 would indicate that projects A, B, and C have 3, 2, and 1 tasks remaining, respectively. This array is updated throughout the recursive process to reflect the current state of the task pool. Second, we use the recursive call stack to manage the state of the algorithm. Each recursive call stores the current remaining_tasks array and the last_project chosen, allowing us to backtrack and explore alternative assignments when necessary. Now, why use backtracking? The main advantage is its exhaustive nature. It ensures that all possible task assignment sequences are explored while adhering to the constraint. However, this approach also highlights an optimization opportunity. If the largest project has more tasks than the combined total of all other projects, it becomes clear that this dominant project will dictate the maximum number of weeks worked. Finally, let's consider some edge cases. For example, if there's only one project with multiple tasks, the result is simply the number of tasks, since there are no other projects to alternate with. On the other hand, if there are multiple projects but each has only one task, the result equals the number of projects, since no consecutive week violations can occur. To conclude, let's evaluate the complexity of this approach. The time complexity is O(n) in the worst case. This arises because the exhaustive search explores all permutations of task assignments across the projects. As the number of projects increases, the number of permutations grows factorially, making this approach computationally expensive for large inputs. The space complexity, on the other hand, is O(n), which arises from the recursive call stack. Here, n represents the number of projects, and the stack depth corresponds to the maximum number of recursive calls, which is equal to the number of weeks worked in the worst case. While this approach guarantees correctness due to its exhaustive nature, its factorial time complexity makes it impractical for large inputs, highlighting the need for further optimizations in real-world scenarios. This solution addresses the problem of determining the maximum number of weeks that can be worked on projects without assigning the same project in consecutive weeks. The number of weeks function takes a list of integers, milestones, where each value represents the number of tasks in a specific project. First, the code calculates the total number of tasks across all projects by summing up the milestones. This is stored in the total_tasks variable. Then, it identifies the maximum number of tasks in any single project using Python's max function, storing this value in max_tasks. The core of the solution revolves around checking whether the largest project dominates the task distribution. If the number of tasks in the largest project, max_tasks, exceeds the sum of all other tasks, total_tasks, max_tasks, this project dictates the maximum number of weeks that can be worked. In such cases, the solution limits the weeks to twice the count of the smaller tasks plus one additional week, ensuring no consecutive assignments to the dominant project. On the other hand, if the largest project does not dominate, all tasks can be completed without any constraint violations. Thus, the total number of weeks equals the total number of tasks. The solution is efficient with a time complexity of O(n), where n is the number of projects, as it involves a single traversal to calculate the sum and find the maximum. The space complexity is O1, as no additional data structures are used beyond simple variables. This approach ensures correctness while adhering to the problem's constraints. This is the Java implementation for LeetCode problem number 1953, maximum number of weeks for which you can work. The logic mirrors the provided Python solution, with the same steps to calculate the total tasks, find the maximum task count, and determine whether the dominant project limits the number of weeks. Key differences include the use of explicit type declarations for variables and loops in Java, as well as Java's math.max for calculating the maximum value. To understand how we can calculate the maximum number of weeks we can work, let's start with a balanced distribution example where the milestones are 1, 2, 3. First, we calculate the total number of tasks by summing up all the milestones. Adding 1, 2, and 3 gives us a total of 6 tasks. Next, we identify the largest number of tasks associated with any single milestone. In this case, the maximum value among 1, 2, 3 is 3. Now, we check if this largest number of tasks dominates the rest. Specifically, we ask whether 3 is greater than the difference between the total tasks and the largest milestone, which is 6 minus 3. Since 3 is not greater than 3, the dominance condition is false. This means that no single milestone overwhelms the schedule, and as a result, we can complete all 6 tasks. Therefore, the output in this case is 6. Now let's consider a scenario where one milestone dominates the rest. Here, the milestones are 5, 2, 1. Again, we start by calculating the total number of tasks. Adding 5, 2, and 1 results in a total of 8 tasks. Next, we find the largest milestone. The maximum value in 5, 2, 1 is 5. Then, we check whether this largest milestone exceeds the sum of the remaining tasks. In this case, we compare 5 to 8 minus 5, which gives 3. Since 5 is greater than 3, the dominance condition is true. This tells us that one milestone dominates the others, and we'll need to adjust our calculation to account for this fact. To handle a dominant milestone, we use a formula to determine the maximum number of weeks we can work. The formula is the difference between the total tasks and the largest milestone, multiplied by 2 plus 1. Substituting the values, we take the total tasks of 8, subtract the largest milestone of 5, multiply the result by 2, and then add 1. This gives us open parenthesis 8 minus 5 close parenthesis times 2 plus 1, which simplifies to 3 by 2 plus 1, resulting in 7. Thus, the maximum number of weeks we can work in this case is 7. Now let's look at another example where the milestones are evenly distributed. Here, the milestones are 4, 4, 4. Starting once again with the total tasks, we calculate 4 plus 4 plus 4, which equals 12. Then, we identify the largest milestone, which is 4, as all the milestones are equal. With the total tasks at 12 and the largest milestone being 4, we now check the dominance condition. We evaluate whether 4 is greater than the difference between 12 and 4, which is 8. Since 4 is not greater than 8, the dominance condition is false. This means that no single milestone dominates, and we can complete all the tasks without issue. Therefore, the output in this example is simply the total number of tasks, which is 12. To analyze the time complexity of this algorithm, we start by looking at the key steps involved. First, we calculate the total number of tasks across all projects, which is done using the sum function. Since this function iterates over each element in the milestones list once, it requires n time where n is the number of projects. Next, we determine the maximum number of tasks in a single project using the max function. Similar to sum, it also involves iterating through the list of size n, and therefore takes n time. Finally, the algorithm performs a simple comparison between the maximum tasks and the remaining tasks, followed by a conditional return. This last step involves basic arithmetic and comparison operations, which are completed in O1 time. When we combine these steps, the overall time complexity becomes n plus O1, which simplifies to n. Thus, the time complexity of this solution is n, where n is the number of elements in the milestones list. Now let's consider the space complexity. The algorithm operates directly on the input list without allocating any additional data structures. The input milestones list itself occupies n space, as it contains n elements. Beyond this, the algorithm uses only a small, constant amount of extra space for a few auxiliary variables such as total_tasks and max_tasks. These variables require O1 space. Since there are no other data structures or temporary storage being utilized, the total space complexity is determined by the size of the input, resulting in n space complexity. When comparing this optimized approach to a naive solution, the improvements are significant. A brute force method would involve simulating all possible task assignments while ensuring that no two consecutive tasks belong to the same project. This approach would explore all permutations of the milestones list, leading to a time complexity of n in the worst case. Such a solution becomes computationally impractical as n grows. In contrast, the optimized solution avoids this exhaustive search by focusing on the core challenge, determining whether the largest project is too dominant compared to the rest. By reducing the problem to a simple arithmetic condition, the algorithm achieves an efficient n time complexity and n space complexity. This combination of mathematical reasoning and computational efficiency makes the solution both correct and optimal, a clear improvement over brute force methods. When working on this problem, there are several common pitfalls to watch out for. One major mistake is not handling edge cases properly. For instance, scenarios like an empty input or the smallest constraints, such as n equals 1, are easy to overlook. On the other hand, failing to account for maximum constraints, like n being as large as 10 to the power of 5, can lead to runtime errors or inefficiencies during testing. A second issue arises when developers attempt a brute force solution on large inputs. Naive simulations or recursive approaches without optimizing the search space often result in exponential time complexities, such as 2 to the power of n, which become infeasible for inputs larger than approximately 15 to 20. Misunderstanding the constraints is another frequent challenge. For example, missing details like no two consecutive weeks can, or tasks must be distinct can lead to incorrect implementations. It's critical to carefully reread and fully understand the problem statement before diving into coding. Additionally, overcomplicating the solution is a common error. Using advanced data structures or convoluted logic where simpler greedy or dynamic programming approaches would suffice only wastes time and increases the potential for bugs. Lastly, while optimizing runtime, some solutions ignore space complexity, leading to excessive memory usage and failures on larger inputs. Balancing both time and space constraints is key to a robust approach. To excel in this type of problem, it helps to focus on a few key strategies during interviews. First, pattern recognition is critical. Many problems like this involve subsets, permutations, or combinations, which can often be tackled using backtracking or dynamic programming with memoization. Recognizing these patterns early on can save valuable time. Additionally, understanding when to use a greedy strategy versus dynamic programming is essential. If the problem involves overlapping subproblems, such as maximizing or minimizing values across consecutive intervals, dynamic programming is typically the best choice. However, if making locally optimal choices leads to a globally optimal solution, a greedy approach might be faster and simpler. Optimization is another important consideration. Once you have a brute force solution, always look for ways to improve it. Techniques like memoization, pruning unnecessary branches, or converting recursive solutions into iterative ones can significantly enhance efficiency. Finally, clear communication is vital during an interview. As you decide on an approach, explain your thought process, including trade-offs like time complexity, space complexity, and how you plan to account for edge cases. This not only demonstrates your understanding but also helps interviewers follow your logic. There are several related problems that you can study to build your skills in solving this type of challenge. For example, LeetCode 198, the house robber problem, is a dynamic programming problem that also involves constraints on consecutive decisions. Similarly, LeetCode 55, Jump Game, focuses on decision-making at each step to achieve a specific goal, which teaches you how to think strategically about sequential tasks. Another useful problem is LeetCode 139, Word Break, which demonstrates how to use dynamic programming with memoization to solve problems involving sequences. Finally, LeetCode 91, Decode Ways, is another dynamic programming problem that deals with constraints on sequences, making it an excellent example for understanding how to approach problems with similar characteristics. Studying these problems can help you recognize patterns and refine your approach to solving constraint-based challenges. There are multiple approaches you can take to solve this problem, each with its own trade-offs. A brute force approach involves simulating all possible task assignments week by week. While this method is straightforward to implement, its time complexity is exponential, 2 to the power of n, which makes it impractical for larger inputs. A more efficient alternative is to use dynamic programming. By maintaining a DP table that tracks the maximum number of weeks or tasks completed under the given constraints, you can reduce the time complexity to n squared, or even n asterisk k, where n is the input size and k represents the constraints. Another option is a greedy approach, which involves making locally optimal choices, such as assigning tasks based on availability and constraints. This method is faster, but it risks failing for edge cases where a global optimization is necessary. Finally, backtracking with memoization offers a balance of flexibility and efficiency. By combining recursion with memoization, you can explore all valid assignments while avoiding redundant calculations. However, it's important to implement this carefully to avoid issues like stack overflow in cases of deep recursion. Each approach has its strengths and weaknesses, so the best choice depends on the problem's constraints and requirements. Great job sticking with us. In this session, we tackled problem number 1953 and explored different approaches to solve it efficiently. Remember to practice similar problems to strengthen your understanding of combinatorial optimization. Thanks for watching, and we'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!